We now move into the third major section, exploration geophysics. This is where we connect physical principles and geophysical data to the workflow of petroleum exploration, including seismic waves, travel times, velocities, processing, interpretation, and modern data-driven trends. Seismic waves are vibrations that propagate from a source through the earth until some of the energy is reflected back to the surface and recorded by receivers. On land, the receivers are typically geophones, and offshore they are hydrophones. The source may be an explosion, a vibrating truck, or an airgun in marine settings. The key measurement is travel time from source to receiver, which forms the basis for imaging the subsurface. This slide compares compressional P waves and shear S waves. P waves move particles back and forth in the same direction as the wave travels, so they are compressional. S waves move particles perpendicular to the direction of travel, producing shear motion. This distinction is extremely important because P and S waves respond differently to rock stiffness, density, and fluid conditions, which gives geophysicists valuable diagnostic information. This slide introduces several basic seismic wave concepts: amplitude, wavelength, compression, rarefaction, and direction of motion. It also notes that typical seismic frequencies range from about 5 to 100 Hz. These ideas matter because seismic resolution and penetration depend strongly on wave frequency and wavelength. Higher frequencies give better resolution, while lower frequencies often penetrate deeper. Here we apply the wave concept to a simple travel time calculation. A seismic wave travels downward to a depth of 2,000 meters at 5 kilometers per second and then reflects back to the surface. How long does it take for the seismic wave to make the round trip? This is answer and solution for you. The downward travel time is 0.4 seconds, and the round trip or two-way travel time, often called TWT, is 0.8 seconds. This is a very important concept because seismic sections are commonly displayed in two-way travel time rather than depth. I have a simple break question for you. True or false? Can seismic waves help find oil and gas in underground? The correct answer is true. Seismic waves help us find oil and gas because they respond to changes in rock properties and subsurface structure. When waves encounter different materials, their travel times and reflection behavior change. By measuring how long the signals take to return and analyzing reflection patterns, geophysicists can create images of underground layers and identify possible traps, reservoirs, and fluid-related anomalies. This slide explains that seismic velocity depends on rock properties, especially bulk modulus, shear modulus, and density. It also explains why P waves were originally called primary waves and S waves secondary waves, because P waves arrive first. The equations shown here are fundamental because they link seismic response directly to the elastic behavior of rocks. This is one reason why geophysics is so powerful. It connects measurable wave behavior to physical rock properties. This example applies the velocity equations to dolomite using given values of bulk modulus, shear modulus, and density. The slide shows a worked solution for calculating both compressional and shear wave velocities. The main lesson is not only the final answer, but the process. Convert units carefully, apply the correct formulas, and interpret what the results mean for elastic rock behavior. This kind of calculation builds physical intuition for seismic interpretation. Are you ready to know the answer? The answer can be seen in the slide. We can replace the suitable parameters in equation and got the results as slide. This is a very important workflow slide. Seismic exploration uses reflected seismic waves to image subsurface structures. The process includes data acquisition, sampling and processing, inversion or imaging, and finally interpretation. Interpretation may involve identifying faults, reflectors, facies, and possible reservoir zones. This slide is valuable because it shows that exploration geophysics is not just data collection, it is a full pipeline from source signal to drilling decision. This slide is a section header introducing current trends in exploration geophysics. The message here is that geophysics is evolving from mainly structural imaging toward increasingly quantitative, data-rich, and machine learning-assisted interpretation. The following slides explain what that means in more detail. Traditionally, seismic interpretation was mainly qualitative. Interpreters manually picked and tracked reflectors across seismic sections to map structure and stratigraphy. The ultimate goal was to identify structures favorable for hydrocarbon accumulation and estimate their size. This approach remains important, but today the industry increasingly wants quantitative interpretation, where seismic amplitudes and attributes are linked more directly to physical reservoir properties. This slide explains why quantitative interpretation became necessary. Qualitative interpretation maps geometry well, but it often pays limited attention to the physical meaning of amplitude variations. Quantitative methods help detect direct hydrocarbon indicators, estimate fluid saturation, and improve reservoir characterization. In other words, the goal is not only to see structures, but to infer more about what those structures contain. Here the deck lists several important quantitative techniques: post-stack amplitude analysis, AVO analysis, acoustic impedance inversion, elastic impedance inversion, forward seismic modeling, and attribute analysis. You do not need to master all of these today, but you should recognize that modern geophysics uses a suite of tools to extract more physical information from seismic data than traditional structural interpretation alone. This slide highlights a central idea: seismic amplitudes contain information about lithology, mineralogy, porosity, pore fluid type, saturation, fluid distribution, and pore pressure. These are extremely valuable reservoir properties, but they cannot be extracted reliably from purely qualitative interpretation. This is why amplitude analysis and rock physics integration are so important in modern reservoir characterization. This slide connects seismic response with rock properties such as acoustic impedance and Vp/versus ratio, and then links those to petrophysical properties like porosity and shale volume. The idea is that different lithofacies may cluster differently in elastic attribute space, allowing geophysicists to distinguish sands, shaly sands, or gas-bearing intervals. This is a very important bridge between seismic interpretation and reservoir property prediction. This slide introduces AVO, or amplitude variation with offset. AVO uses pre-stacked seismic data and studies how reflection amplitude changes with offset or incidence angle. These variations are related to changes in acoustic impedance and the Vp/versus ratio across interfaces. AVO is a powerful reservoir characterization tool because it can provide clues about lithology and fluid type, especially for gas-charged sands and other fluid-sensitive targets. This slide introduces the use of classical machine learning in geophysical applications. Traditional wave equation-based methods remain fundamental, but machine learning offers a complementary, data-driven approach for regression and classification. The slide emphasizes the combination of rock physics plus machine learning for reservoir characterization. This is especially relevant today because industry workflows increasingly mix physical models with data-driven prediction. This slide moves from classical machine learning to deep learning. The key idea is that deep learning can help overcome some limitations of traditional methods, especially in pattern recognition, complex feature extraction, and automation. In exploration geophysics, deep learning is now being explored for denoising, velocity inversion, fault interpretation, and other tasks. It does not replace physics, but it can improve speed and efficiency in many workflows. Seismic data are often contaminated by random noise, ground roll, and multiple reflections. Traditional denoising methods use handcrafted filters or regularization, but these can fail when signal and noise share similar characteristics. This slide explains that deep learning has been used successfully to remove scattered ground roll and improve signal-to-noise ratio. This is a very practical example of how AI can help exploration geophysics. This slide shows that tasks such as seismic interpretation and attribute analysis are often accurate but time-consuming because they require expert intervention. Deep learning can help automate or accelerate these tasks, for example by detecting faults or extracting patterns from 3D seismic volumes. The key message is that deep learning has strong potential to improve both efficiency and interpretation consistency in geophysical workflows. This slide is a section header. It signals that the future of exploration geophysics will likely involve tighter integration between traditional physics-based methods and data-driven deep learning approaches. The following slides elaborate on that direction. This slide asks four important future-oriented questions. Can traditional and deep learning approaches collaborate? How can deep learning be incorporated into traditional methods? How can traditional methods be embedded into deep learning? And how can the two cooperate effectively? These are excellent questions because the most promising future workflows will likely be hybrid rather than purely physics-based or purely data-driven. This slide introduces multimodal deep learning, where inputs come from different data sources such as seismic and gravity data. Using multiple geophysical modalities can help reduce data limitations and improve prediction robustness. In other words, instead of relying on only one type of measurement, future geophysical AI systems may integrate several types of evidence to build more reliable subsurface interpretations. This is a creative engagement slide. It asks what form of art comes to mind when we see Hertz, or Hertz, and how that might relate to geophysics. The intended bridge is sound and music, since seismic data are wave signals and frequency is a central concept in both geophysics and audio. This slide is a nice reminder that wave-based data can sometimes be understood not only scientifically, but also intuitively through sound and visual pattern transformation. This slide takes the geophysics and art idea further by showing a seismic trace, a spectrogram, and a piano roll-style display. The message is that seismic signals can be transformed into alternate forms of representation, including music-like formats. While this is conceptual, it is also a good teaching device because it helps students understand that seismic data are fundamentally time-varying wave signals with frequency content.